Okay, guys, we're going to begin to advance our understanding of what we know about light. We know about wavelengths and frequencies, and we know how to calculate the relationship between those. But now we're going to actually really see where light comes from. Okay, so to do this, we must understand the Bohr diagram. Now, remember that Niels Bohr was the person who proposed that electrons were we're orbiting around the nucleus in these specific energy levels, so these shells. Now you've probably seen these shells in middle school before, where you have your protons and your neutrons in the nucleus, but we're really just going to ignore those, and we have our energy levels. Those are those circles. So there are 3 energy levels here. We're going to say that this is the nucleus. So there are 3 energy levels. So the first energy level holds 2 electrons, the second energy level holds 8 electrons, and the third one holds 18. So that's probably what you have learned in middle school, and that's about it that you covered so far. So you had 2, 8, and 18, like so, and you filled them in. We will progress to a point where there's like things, some extra stuff, but we're going to check this out in a second. So now these outside electrons are called valence electrons. So that's important definition to know. Outside is the valence, and the inside electrons are called the core electrons. So valence electrons are the ones in the highest energy level. Okay. Yeah. So we take these valence electrons sometimes and we write what we call a Lewis dot structure. We'll get into more of this later. But if you're just going to write an element, you just write the element symbol as an X, and then you write the number of valence electrons around it. So right now we won't have any more than 8. And so what you do is you start with the first one here. 1, 2, 3, 4, 5, 6, 7, 8. So you go clockwise and you place them that way. That's the best way to do it, because they start pairing up, and you want to make sure that they pair up in the right ways. So let's check this out. Bohr diagrams. So with lithium, it has, if you look at its electrons, it has 3 total electrons. So it will have 2 on the core electrons, and will actually have an outer electron. So the electrons always fill in from the lowest energy level possible, and then once this one is full, then you have to move on to the next energy level. So that has 1 valence electron, and so its Lewis structure is going to just have 1 dot on it. Now for nitrogen, it has 7 electrons, so we'll place our 2 in the middle, and then we'll fill up the ones on the outside. So it has 5 valence electrons on the outside. Okay. Now, so nitrogen, we will take 1 dot and another dot, another dot, another dot, and then boom. And we has 5 valence electrons here. 2 of them are paired up, and then it has 3 single ones like this. So that it is important that we do that, because it's going to end up making 3 bonds later on. So when we get to bonding, that's going to be important that you draw them the correct way. For magnesium, we fill up our core electrons first, and so that's 12, not 12 yet, and you should have 2 valence electrons here. Okay, so you would put 2 valence electrons like so, and then beryllium is like that as well. Okay, sulfur has 6 valence electrons as you fill in those dots in your Bohr diagram, and then you have sulfur, just like so. Okay, so sulfur normally makes 2 bonds because it has 2 open or 2 available electrons for bonding. And then carbon normally has 4 bonds because it has 4 electrons available for bonding. Okay, kind of cool, right? And neon is your noble gas. So check it out. It has 2 valence electrons filled up here, and then it has 8 filled up in this outer shell. So it is at what we call a noble gas configuration. So it has 8 valence electrons, which means that it is a completely full Lewis dot structure. It cannot take any more bonds. It doesn't want to bond with anything. So as a very happy atom, it is at its Lewis noble gas configuration, is what we would say. And then argon is going to be the same way, except they are filled out on the outside as well. Okay? So let's get to the origin of light. So there's a couple of definitions here. In page 5 of your notes, the lowest possible energy level is its ground state. Okay? And then the state in which an atom has a higher potential energy than it has in its ground state is called an excited state. So we have the ground state and we have the excited state. This is the lowest energy level possible. And then anything higher than the ground state is called the excited state. So let's check this out. Let's just pretend that this is hydrogen and this only has one proton and one electron. So it has its ground state is going to be at the closest energy level possible, right? Now what we can see is that in an excited state, if it's given a little bit of energy, it can move to a new energy level, right? If I add some heat to it, I can move it to an higher energy level, which is the excited state. Now, when the excited state, now they're not stable in this excited state, so they will fall back to the ground state. But when they do, they will emit a photon, because there has to be that conservation of energy. It absorbed energy, so it moved up to the higher excited state. But then when it goes back down to lower energy, it has to emit some energy, and that is the photon that's being released. Now this photon is this light that you are seeing, traveling like a wave, just like so, and it's at a specific wavelength. So that is responsible for the color that you see when you look at hydrogen. If you burned hydrogen, hydrogen has a specific color because of this specific photon that's being released at a specific wavelength. Very, very cool. So all atoms kind of do this. So I'll go back to that one more time because it's really helpful. So we're in the ground state, and then when we add some energy, it will jump to the excited state, and then while it's in the excited state, it's not stable, so it will fall back to the ground state. And that difference in energy from here to here is the energy of the photon that's released. Now, energies have specific frequencies, and energies have specific wavelengths, right? That's what we learned in the previous lessons about wave calculations. So we now know that we can tell the energy of the photon just by its wavelength or its color, because wavelength and color are the same thing. Okay, so classical theory would say that when electrons were like this, that you would get a continuous spectrum right here. But the observations would show that we only get discrete wavelengths. We only get 4 specific wavelengths for hydrogen. We get a few more for helium, and I'll show you some more later. So what is happening is we're figuring out that electrons can't exist anywhere in between. They have to exist on these actual energy levels. This is what we call quantized. They are quantized values. So here, we end up coming up with 3 series. This is the Lyman series, where there are jumps from any level down to the first energy level, which is this one. And then we have the Balmer series, which are jumps from any excited state down to the second energy level, which is right here. And then the Paschen series, which is any jumps down to the third energy level. So now you don't have to know the names of them, but the Lyman series is ultraviolet light because they have the biggest jumps, so it's going to have the most amount of energy. The Balmer series is the visible light. It's kind of in the middle. And then the Passion series is the infrared light because it has the smallest jumps. So it has the least amount of energy. So the circles here aren't exactly to scale. So that may be why that might be a little confusing. But this is the best description for that. So this is n equals 1, this is n equals 2, and this is n equals 3, the energy level. Okay, so in your notes, go ahead and write down specific ones. So page 6 of your notes, right there. And then also in page 6. So the puzzle of this hydrogen atom was solved by the Danish physicist Niels Bohr. He proposed a model of the hydrogen atom that linked the atom's electron with its photon emission. According to the model, the electron can circle the nucleus only in allowed paths or energy levels. So this is where we get the term energy levels. It's from Niels Bohr. When the electron is in one of these fixed orbits, the atom has a definite fixed energy. The electron, and therefore the hydrogen atom, is in its lowest energy state when it is in the orbit closest to the nucleus. The orbit is separated from the nucleus by a large empty space where the electron cannot exist. The electron cannot exist anywhere in between. The energy of the electron is increased when it is in orbits that are successively farther from the nucleus. Okay? So, what determines the color of light being released? It is determined by how big the jump is. So we have a bigger jump here, so it is going to be a bigger jump, so it's going to have a longer wavelength. A shorter wavelength, which is a higher energy. A middle jump, which is a little bit longer, so it's going to be a little bit lower energy. And then a smaller jump is going to be a much longer wavelength, which is going to be a lower energy. So the lower energy, that's going to be the red ones. And then we would get to up to violet or blue right here. Okay, so the colors really come from which energy level it's coming from. It's kind of cool. You can actually look at the width of an atom just by looking at its colors. So we can measure this through a method called spectroscopy. It's the study of light given off by an excited element. So we use a spectroscope, and I have a bunch of these in my classroom, and it's used to separate light into a spectrum, and it's really just a prism to be able to look at it. Now, if you go out and look up at the sun, well, not directly at the sun, but if you look at sunlight, you get a continuous spectrum right here. So that's because of all the things that are in the sun and a lot of astronomical reasons, but you get a continuous spectrum. Now, if you look at just specific elements that are burned, or that are look at just specific elements, you get these lines. So you can actually use spectroscopy to identify specific elements, which is really cool. That's what our flame test lab is about. So we have hydrogen here. It has a specific spectra. Sodium's is here. Here's helium. Here's neon. So we got more electrons. So we get this. And then here's mercury. Now, this is the whole periodic table. And I just think it's really cool to look at. Notice how the ones down here don't have that many electrons. Probably because they haven't been tested. Right here. But all of these guys, these transition metals, it's really cool how 1, 2, 3, 4, 5. So like the first 5 right here have a lot of wavelengths, and then it starts to taper off in the second group of 5. Is there a reason for that? Actually, there is, but we'll get to that. Mostly in your AP or IB chemistry course. Okay. So we can actually put this on a test question where if you had a bunch of spectrums right here and you have different gases, you could compare it to an unknown mixture. So what does this mixture have? So it's got some of gas A, right? Well, this one, it's got some of gas D. Oh, sorry. It's got some of it gas A again. You see where gas A's lines are? It's some of gas A. And this one right here. And then this line, these lines match up with gas D. So this is a mixture of gas A and gas D. So very cool how you can identify elements just by their spectra. So here's your check for understanding. Go ahead and try it out. We know helium's there. And so now we can tell that hydrogen is there. All right. Well, that's going to be it. I hope you'll have a great day.